Okay, today we're going to start chapter 4, algorithms. In this chapter, we will start with the examples of algorithms. Then we will have some analysis of algorithms. And then the recursive algorithm. 이게 점화식이죠. We will cover the recursive algorithms in this chapter. The term algorithm comes from the name Al-Khwarizmi, the Arabian mathematician, and the word algorithm was used for the rules for performing arithmetic using decimal notations. The algorithm evolved into the word algorithm that we are using now by the 18th century. And this is the kind of grading scale that you can expect. Okay, the algorithm is a step-by-step method for performing a computation or for solving a problem. Okay, algorithm has the following characteristics. It should have input. Okay, it should have input values from a set. Then it should have output. The algorithm produce the output. And the algorithm should have a definiteness. Each step of algorithm must be defined precisely. And also, algorithm should be very effective. It must be possible to perform each step of algorithm exactly and in a finite amount of time. Should be. And the algorithm should have a finiteness. The algorithm shouldn't have an infinite loop in it. And correctness. Algorithm should produce the correct output values for each input value. And generality. The procedure should be applicable for all problems of the desired form. So the algorithm should be used for the general problems of a certain criteria. Okay, this is one example of algorithm. Okay. This algorithm 1.1 is to find the maximum of three numbers A, B, and D. Suppose we have three numbers A, B, and C, then this algorithm that gives us, we define the input, then among these three numbers, let's define the first one as output, and then if B is bigger than the first one, then let B be the designated output, and then go check the C number with that designated output. If C is bigger than the earlier one, then gives output as C. If not, then goes to the next one. Okay, so we can check those in here. So this is the algorithm that was written in the textbook, and I retyped it in here. So we defined ABC, and I typed the code which is written there. If we execute it, evaluate it, then among these three numbers, it gives us the largest one. If we change those numbers, then this algorithm gives us the largest one among these. If we have another number like that, then this algorithm gives us the largest one among those. So this is a very simple algorithm that can be performed by this code. Next algorithm is finding the maximum value in a finite sequence. Find the maximum value among these n numbers from S1 to Sn. Okay, here. This is the code which was introduced, and I typed this in here. So we give 6 numbers. We define 6 numbers here, and n is the length of those numbers, the list of the set, and define the large as the very first one. The index starts from 0. So and we check whether the next one is larger than the first one. If it is bigger than the earlier one, then we redefine it as the large one and then go through it. Then the final output will be the largest number among the given. For example, here, if we have these numbers, 6 numbers here, then as you see, this algorithm gives us the largest number among these. If we change this number, or if we give the other numbers, so if you have these numbers, then that same algorithm gives us the largest number among this. Okay, Mr. Nabil, got it? So whatever number you gives here, then it will gives you those. If you replace this set here, then you will have like this. If you change the code, then you will see. Okay. Anyway, this is it is a very simple code. This okay. This is the one of the example of the algorithm that you can see. Okay, next. That was the introduction of algorithms. Next, section 4.2 tells us the examples of algorithms. First one was searching. The problem of locating an element in an ordered list occurs in many contexts. The first algorithm that we will present is called the linear search or sequential search algorithm. Okay. If you have the list of the numbers, then this linear search algorithm make those numbers in the order, and this gives us this code gives us the number that we are asking is where the number is located. So this algorithm tells us the number that we have is is location of the location of the number that we have. For example, among these numbers, the number 4 is in the third positions, like this. Suppose we have these numbers, then okay, let's do it in here, and the 4 are here. Okay. Like this. If we have these numbers, then the number 6 is in the fifth position in this order. So in here, like 777 is where it is. It is in the 8th position from the beginning. Okay. Here, the index started from 1, but we started with 0 because Python language counting the very first one was 0. It starts from 0, not from 1. So that's why I made the minor change, so it gives us the exact position we are looking for. That modification was made. All of this code can be found in. These are the whole code that you have seen it. It gives you the number of the location of the given number in the list of the numbers which was given. Okay. Next, binary search. Okay, binary search. This algorithm can be used when the list has terms occurring in order of increasing size. When the number with the list has terms occurring in order of increasing size, then this binary search algorithm performed in this way. Okay. Let me show here. If the terms are numbers, then they are listed from smallest to the largest. And if they are words, then they are listed in lexicographic or alphabetic order. Okay. For example, to search 19 in this list, then this binary search algorithm works in this way. Divide the whole set as half and compare the very last one with the given one. So 10 and 19. So 19 is bigger than 10. Then ignore this part. And then just 19 is in here. So we compare the numbers 19 with this. So we divide this half to the another half and compare this 16 with 19. And as you see, 19 is bigger than 16, so we ignore the first part and we only compare with this last quarter. Then divide this as half, then compare the very last one in the first half with the given number 19. As you see, 19 and 19 are same, then this algorithm terminates. So that gives you where the number 19 is located in the list, the locations. And this is the algorithm. Here we did use the floor function. Okay. We divide it by half and compare the given number with this number and do compare the last one of the first half to the given one to decide the next step. And this is the algorithm. Here we show the linear search algorithm. Yeah, you have seen that occasion. And this is the binary search algorithm. Here, as you see here, if you have the list of numbers in the increasing order like this, then as you see, with this algorithm, gives you 19 is in the 14th position among the list. With that, for example, 12 or 22, then it shows 22 is in the 16th position, and 6 is in the 5th position. This was done by divide this as half and compare this one and this one is smaller, then ignore the last part and then divide the remaining half to the another half and compare that to 6 and it's not in here, then it goes here and divide it and compare to 7 and 6 and then divide it once again, then 6 and 6 are same. So this is the way. That's the algorithm. In that case, we did use this plural function that we defined in the earlier chapter. Okay, Mr. Wang Zhaoxiang, understand?
Yes.
Okay, so this is very simple, but after a certain step, we can easily can tell where that number is located. The convergence speed is very fast because we just cut it off the half and half after a certain iteration, that we will have only a couple of numbers left to be compared. Okay, next, sorting. Sorting is putting these elements into a list which the elements are in increasing order. Suppose we have a bunch of numbers without order, then we like to make it an order. We like reorder those given numbers in the increasing order. In that case, this sorting algorithm can be used. The first example is a bubble sort. Bubble sort is one of the simplest sorting algorithms. And we will introduce one more sorting algorithm. Each of those has some advantages and also disadvantages. If it has all the advantages and without disadvantages, then we don't have to learn any other algorithms. The reason that we are learning the several different algorithms for one purpose is each algorithm has some advantages which works very well for certain type of the data, but the other algorithm work better for the others in the other category of the input data. Okay, bubble sorting is like this. Suppose we have a number 3, 2, 4, 1, 5 like this, then just compare the first two. If 3 is bigger than 2, then switch these numbers like this. And then compare this 3 and 1, and then 3 is bigger than 1, then switch it like this. And compare 4 and 5, and then so it's in the increasing order, so you don't have to do. Then next, go back here. Compare 2 and 1, this is reversed, so switch it like this. And if you do that over and over again, then at the end you will have the numbers in the increasing order. Okay, just to switch, just to move, just to find the right place of each number, and then do the next iterations one by one. So this is very tedious, but eventually it will be ended to make the list of these numbers in the order of 1, 2, 3, 4, 5. Okay. So this is the algorithm for that bubble sort. And this is another algorithm, insertion sort algorithm. This is also a simple sorting algorithm, but it is usually not the most efficient, like the bubble sort. But this works also quite well for many cases. Suppose we have input numbers like from S1 to Sn. The sequence is to sort the data in non-decreasing order. At the ith iteration of insertion sort, the first part of the sequence from S1 to Si will have been rearranged so that it is sorted. Like if we add one more number, I plus 1. So you start from S1 and you add S2, then to make a sort. Then add S3 to make a list. Then add S4 to make a right position for that number. Then S5, S6. You just add each numbers to make all the list. Understand? So if you have a bunch of the numbers, then you just put the number at one at a time. Just insert it. You just add the number to make an order. Then at the end, they will be all rearranged in non-decreasing orders. If some numbers are same. This is the way. For example, in the middle of the stage, suppose we have 4 numbers in the order. After 4 iterations, if we have these 4, the next number is 16. Fifth term is 16. If you want to find the position for the 16 in this, then after a certain period, it will find their positions like this. How? To insert 16 in this, just we first compute this input number with the very largest number in here. If this 16 is greater than 27, then you just add it at the end. But if not, then make an empty space before 27. Okay, and then compare this 16 with 20. If it is not in the increasing order, then you switch it. You just move this 20 to the right and make an empty spot before 20. And then compare this 16 with the earlier number 13. If it is in the non-decreasing order, then that's his place. So put that number in here. So it will find its own place. So it will be reordered like this. Similarly, if you wanted to add S6, if you want to find the position for the S6, then suppose S6 is 9, then you do the same thing. You start compare to this, and then compare the next to find the number in between 8 and 13. That's the insertion algorithm. Okay, this is the code that I made. I'll show you here. Insertion. This is insertion. Suppose it was sorted in this. We did that insertion algorithm. The 20. First one was 20, and next 13 was added, then 27 was added in that with that algorithm. If you have the more numbers like this, something like this, then you will have the numbers like this. So if you have a big, large data, so still you can order it like this, okay, without bothering. Even though you have a million numbers in here, that algorithm gives you all those million numbers in the order in 1 second. Okay. Next. Time and space for algorithms. It is important to know or be able to estimate the time and speed required by algorithm. Okay. Best case is this situation. The input sequence is already sorted in non-decreasing order. Then it will perform effectively. The input sequence is sorted in decreasing order. Then the loop will execute the maximum number of times. Do you understand the difference? Suppose the input data is already in the increasing order or non-decreasing order, then that algorithm will quit very quickly. But the original data is not well ordered. If it's in decreasing order, then every number have to do the iteration as maximum number of the comparing those things. So the computing time will be maximum. Okay? So whenever you do execute some algorithm, it's important to start with the well-ordered input data. So this algorithm is useful before we start to any other real algorithms. And also, we need to relax the requirement of a given algorithm in order to use our computer effectively. We call it is a relaxation, the requirement of an algorithm. So the algorithm should have finiteness. If the algorithm has no finiteness, then the operating system never terminates. It will learn over and over again. So you won't be able to get the output. So your algorithm should have the finite number of iterations. So you should fix the algorithm to have this finiteness. So you should know it will be ended at certain time. You should expect it. Determination. The algorithm should have determination. If it doesn't have it, then you should fix the algorithm to have determinism. Algorithm for multiprocessor machine or distributed environment are rarely deterministic. So we should check the algorithm to make sure it is deterministic. And also generality or correctness. The many practical problems are too difficult to be solved efficiently. So with a certain condition, if you put the data, then we should be guaranteed it works with that algorithm. So that algorithm, the algorithm that we're going to use should have a generality for certain type of all problems in that category. So not only very specified case. Okay. Next, randomized algorithm. The randomized algorithm does not require that the indeterminate of each step of execution be uniquely defined and depend only on the input and result of the proceedings. Okay. By definition, when a randomized executes at some point, it makes random choice. In practice, a pseudo-random number generator is used, like this. This is the random number generator, which returns a random integer between integer I and j. Okay. This command randomly generate a number in between I and j. Okay. Sometimes you need to choose the random numbers to execute the algorithms. And this is the shuffle algorithms, and that you take a look, and also this was left for the exercise program for you. Next, analysis of algorithm. Analysis of algorithm. Okay. Use list program for certain type of input is this. Even though derived from a correct algorithm, if the time needed is too big, then it's useless. If it takes too much of time for a certain algorithm, then even though the algorithm is correct, it's not useful. It will take too much time. If the space needed to hold the data is too big, then that algorithm is useless. So when we develop our algorithm, the algorithm, we should make sure the time needed is not that big, and the space needed is not big too. So those are the kind of things that we should have in mind. Here's the examples. Let X be a set of n elements. Some elements are labeled red, and some labeled black. So we have an element with red labeled and black labeled, some of them. Find the number of subset of X that contains at least one red item. Since a set that has n element has 2 to the n subsets, the program would require at least 2 to the n unit of time to execute. 2 to the n. This is a pretty big number. Why? Why it is useless? What if n is very big? What's the situation? These are the situations that you can expect. Here, I will show you. Analysis of algorithm. Okay. Here. Okay. Yeah, these are as n goes to high, then the number of iterations will increasing dramatically. High, big, as you see in this table. Okay. For example, the input is set containing L element, then size of the input is n is n. Yeah, that's the definition. Then best case time is we can ask for the minimum time needed to execute an algorithm among all input of size n. Then we call this time is this is the best case time for input of size n. The worst case time is we can ask for the maximum time needed to execute the algorithm among all input of size n. Then this time is the worst case time for input of size n. And average case is the average time needed to execute an algorithm over some finite set of input of all of size n. So, yeah, we could think about the minimum time needed for certain algorithm. We could count the maximum time needed for that algorithms, and also we can think about the average time needed for certain algorithms. Okay, so in this section, yeah, we learn how to estimate this the time needed for a given algorithm. Example 3.1. A reasonable definition of the size of input for algorithm 1.2, choosing the location, and find the largest value. Find the largest value in a finite sequence. That was the algorithm 2. Find the largest value in a finite sequence. That is the number of elements in the input sequence. Okay. The reasonable definition of the executed time is the number of iteration of the while loop. Okay. This is the algorithm can be analyzed for time by counting that how many times this while loop can or have to perform. With this definition, for algorithm 1.2 for input of size n, then the loop is always executed n minus 1 times. That will be enough. That will be enough to find the maximum, because you have already one. You have n minus 1 other element to be compared with 1. So you just compare maximum at n minus 1 times to draw the conclusion to say which one is the largest value. Okay, then how the best case or worst case time grows as the size of the input increases. For example, suppose an algorithm, this t of n is equal to 60 n squared plus 1. For large n, the term, this 60 times n squared is approximately equal to t of n. This constant doesn't affect much on those iterations. As you see in the table, 60 times n squared plus 5n plus 1, when n goes to big, that will be about this, 6,000 million. And 6t n squared is this. So as you see, there's not much difference. When n goes big, the next two terms, with or without, there's not much difference as n goes. So important thing is this largest term of highest order. Okay? So the other terms are not important. Okay, so we now make a definition on some notations, such as big O notations and big omega notations and theta notations. Here's the definition of big O notation. Let f and g be functions with domain n, which is equal to natural numbers from starting from 1. And if the function f of n is called, it can be written as a big O notation of gn, if and only if we call it fn is big O of g of n, which means f of n is of order at most g of n, which means there exists a C1, constant C1, which is a positive constant number, such that absolute value of fn is less than or equal to C1 times absolute value of G of n. Suppose you can find the constant number C1, positive constant C1, which makes these inequalities, then you can say this f of n is big O of this function G of n, big O. If you have opposite direction like this, and then if suppose there exists positive constant C2 such that absolute value of f of n is bigger than or equal to C2 times absolute value of Gn, then we call this f of n is omega of G of n. Big O and omega. Okay, if this C1 and C2 are both exist, if f of n is big O of Gn and omega of Gn, we just write it as this and call it f of n is theta of G of n, which means the number of iterations eventually same, almost same. Counting the function G of n with the computer is almost the same amount of iteration is needed to do the same computation for the function f of n. That's what it means. Okay? This is a big O notation is very useful. Well, you will see it over and over again. The definition 3.2 can be loosely paragraphs as follows. Okay, is here f is bounded above by function g, or g is a asymptotic upper bound for f, for big O notation. For omega notation, we call f is bounded below by function g, or g is an asymptotic lower bound for f. So f is bounded above by f if we have a g for the big O notation, and bounded below, it has a lower bound by g when f is the omega of g. And also if it is theta, then f is bounded above and below by g. If f is a theta of g, then f is bounded above and below by g. So in this case, g is asymptotic tight bound for f. We call it in this way. This is another notation. This big O notation has an interest. Is so important. So we may take a look on the history of this notation. Big O notation has been used in mathematics for more than a century. Paul Bachmann first introduced the big O notation in 1892. Okay? And it was popularized by Donald Knuth, who also introduced the big omega and the big theta notations. Okay? Donald Knuth is a kind of computational guru. Among many specialists. Okay, here's the example 3.3. Show that 3 times n to the fifth plus da 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 is equal to is theta of n to the fifth power. Why? 3 n fifth plus is less than or equal to this, because n is a natural numbers, okay, and which can be written as 22 times n fifths. So this is less than or equal to 22 times n to the fifth. So if we define C1 is equal to 22, then this function is big O of n to the fifth. Okay, it's bounded above by this n to the fifth. Also, this left-hand side is always bigger than or equal to 3 times n to the fifth. Okay, so if we take C2 is equal to 3, then this n to the fifth is a kind of lower bound for this function. Okay, so we have a C and C2. So it is a big O function of f and also omega function of the n to the fifth. So you should have a theta function. this equation is theta of n to the fifth, which means the iteration of this function is almost the same as the number of iteration of this is almost same as number of iteration of this n to the fifth, not difference. That's what it says. Okay. Let's take a look on it. Big annotations. For example, here we checked it. Prove this function. Prove P of n is equal to AK times n to the case plus a case minus k minus 1 times n to the k minus 1 plus dot dot dot. This is a theta of n to the case. Why? This function, if we define C1 as this, then this P of n is less than or equal to C1 times n to the case, clearly. So C1 doesn't exist. So it's a big O of n to the case. And if we define C2 is equal to AK, this P of n is always bigger than or equal to only the first term, because the others are n is a natural number and these are bigger than 0. Okay, so the C2 does exist. So it is a omega function. So we have C1 and C2. So this function P is a theta of n to the case. Clear? What that means is this: when you have the function, linear functions or log functions like this, then it like this. Let's draw the pictures. Okay, here. This is a linear functions and log functions, but this is exponential functions like this. The number of the iterations increasing dramatically here when the k is bigger than 1. Okay, so we wanna have the iteration which has at least linear like this, or at most this much, not like this. Okay, actually this is also called the NP complete problems in computational science. NP complete problems based on the analysis of this NP complete or NP hard problems comes from here. Show that the 3 times n square plus 8n times log n is a theta of n square. Why? Let log n is log 2 of n, the logarithm of n to the base 2. Okay, we know log n is less than n for all n. You can easily, as you see from this graph, this is always below the y equal x. So this can be, this is less than or equal to n, 3n square plus 8n square, which is 11n square. So there exists 11, which is C1. So clearly the given function is a function, the big O of n square. And also 3n square plus this is bigger than or equal to 3n square for all n bigger than or equal to 1. So there exists C2 does exist. Okay, so C1, C2 both exist. So this function is omega of n square. So that's the theta. So we have both. So this given function is theta of n square. And next, this function is theta of n square times log n. Like what you see, we can find the inequality. This can be written as this, and this can be have a upper bound like this with this function and this constant. So if you choose C1, C2 as this, then it is omega of this function. And find the less inequalities. Here, easily you can find the C1 from here, which is n square. So it's omega function. You can find C2 here. So it is a theta function. So it's omega function. Big O and omega. So it should be a theta over n square times ln over n. All these the prove okay, here, and also here. The summation of all this is a theta of entity force, because summation of this can be is less than or equal to n force, so the C1 is equal to 1, so it's a big O function of entity force, and as you see, this is bigger than or equal to 1 over 4 times n force, so this C2 does exist, so it is omega function, so it is a theta function. As you see, this summation, as you see, this is depend on, so when you add all this, and it can be written as this summation, and all is depend on this highest order degree polynomials, and so we can easily say this left hand side is depend on this. It's omega function, and also big O function of this entity force. And what about this? Summation of this is this, which can be written as the summation of this function is can be found in here. As you see, this is depend on entity cube. So this is the theta function of n cube easily. Okay, and also if f of n is equal is a big O function of Gn, if G of n is a big O function of Hn, then clearly f is the big O function of H. The reason is since of this from the definition of big O, there is C1 that satisfies this, and from the big O notation there exists constant C2 that satisfies this, which means for absolute value of f of n, which is less than or equal to C1 times C2 times absolute value of h of x. That means we have this constant C1 times C2 that satisfies this, which means f is a big O function of h with this constant, new constant c, which is a product of C1 and C2. So that's why we can write f of n is a big O over h of n. Okay, there's the next definitions. Okay, it goes, and these are notations. I fixed this. Yeah. This is an old textbook problem, and this is a new textbook problem. And I showed you, and I also showed you. So if you can compute it, you can easily find the C1 or C2. Yeah, we covered that, and we showed this. Okay, and here. Definition 3.11. If an algorithm requires T of n units of time to terminate, in the best case for an input of size n, and T of n is big O of G of n, then best case time required by the algorithm is the order at most G of n. We know it. The iteration does not exceed the iteration for this function. The best case time requires by the algorithm of this big O of G of n. So if you have information of this iteration, then we don't have to worry much about the iteration for T of n. Okay. Then worst case time requires by, if we have a T of n is big O of n, big O of G, then the worst case time required by the algorithm is of order at most G of n. So we know, yeah, if we have information of the iteration for G of n, then we don't have to worry about it. The iteration on G of n, we can easily expect it. Okay, the average case is same, so at most. So if this the big O, sigma, big O, or omega, and theta notations are useful since for the new functions T of n, when we have information for this function, well-known functions G of n, such as the x to the n, the logs and exponentials, etc. Here's the example. Here's the algorithm. An algorithm is this unit of time to terminate the worst case for input of size n. Why? We show the example, and this is a big O of the theta of n to the fifth already here. So the worst case time required by this algorithm is at most this. And this is the algorithm for the above. Yes, here I can show you in here. Okay. This is algorithm, and this is search algorithm to unordered sequence and matrix multiplication orders. And this was and also this is matrix computation. Matrix computation can be done with this code, and this is common gross functions. Here, this table shows us some ideas of this theta form of each functions, how it behaves. Theta of n square, theta of 1 is a constant. Theta of n is a linear function, like y is equal to x, and theta of n square is like y is equal to x square. So it's a quadratic. Theta of n cube is a cubic, x square, x cube. Yes. So if you have a set of nk, then it's a polynomial times. If it's c to the n, then which means this is the exponentials, the iterations. Factorial, theta of n factorial is a factorial gross functions. And estimate log n factorial is theta of n times log of n with base 2. And this already this much of work was done. So with this in mind, if we can find C1 and C2 to compare with these functions, actually most of functions can be compared with this. Then you don't have to, you can easily expect how much time will be needed to execute an algorithm for certain function T of n. Okay, and the last section is recursive algorithm. Like a factorial. Okay, a factorial algorithm gives you n factorial is start from 1, and next multiply the 2 on here, and the next multiply 3 on that earlier one, and multiply 4 on the earlier one, which is a product of previous 3 numbers, and then multiply 5 to the earlier one, which was a product of earlier 4 numbers, and do it over again until the last product of n on the earlier one. And this can be shown in here. Here, factorial. So this is the algorithm, factorial, that I showed you. Start from 1, then multiply 2 on here, and multiply 3 on the product of these 2, multiply 4 for the earlier product of 3 terms, and go over again until it ends at the end. So that is the factorial that you have. As you see here, 10 factorial gives you this. 55 factorial is like this. 100 factorial the factorial is going to increasing dramatically, a lot bigger than the polynomials. Okay, factorial is so when you have these factorials, then you should expect it will take a lots of times to compute. Okay, next, the algorithm for 2 returns to the value of n factorials. Okay, as you see, yes, this is a proof, mathematical induction proof for this algorithm works. You know it, you have learned it. And next one is a robot can take of 1 meter or 2 meter. Robot can take 1 meter or 2 meter by one step. We write an algorithm to calculate the number of ways the robot can walk n meters. The robot moves from here to n meters. How many ways to reach there? Okay, so here's the sequence of steps. Robot in one distance, if n is equal to 1, there's a one choice. When n is equal to 2, then the robot can take 2 1 steps or 1 meter step or just 2 meter 1 step. For 3 meters, there are 3 ways like this. For 4 meters, there are this many. Then at 100, then how many ways to reach the 100 meter by the robot working? So that's the algorithm that we can think. First work is 1. If we define the work of 2 is 2, then the robot begins by taking a step of 1 meter, like this, here. Yeah, robot begins by taking a 1 meter step. Then a distance of n minus n meter remains. If we go 1, then n minus 1 meter remains. Then if we have the number of ways to reach n minus 1 meter, then all we have to just add it. Next, so the robot, if it begins by taking 2 meter step, then distance of n minus 2 meters remains. If we analyze in this way, there are only 2 cases to be considered. So with this keep in mind, then the work must begin with either 1 meter or 2 meter step. So all the ways to walk n meters are accounted for this. Work of n is the work of n minus 1 plus work of n minus 2 meters. The number of ways to reach n meter is number of ways to reach n minus 1 meters, and work of the number of ways to move to n minus 2 meters from these observations. So this gives a kind of recursive relations, 점화식 recursive relations. Okay, the base case was n is equal to 1 and 2, as you analyzed in here. With this in mind, we made the robot working algorithm. This algorithm computes the function defined by this. When n is equal to 1, it goes 1 meter. When n is equal to 2, then it goes to 2 meters. Then work of n is defined with these recursive relations. Then we code those with those algorithms. Okay, work of n. The work of n is if n is equal to 1 or n is equal to 2. Okay. Then returns n, then return work of n minus 1 plus work of n minus 2. Add this. We start from 1 and 2 and just go through it. Then we will find the W of work of 1 is equal to 1, work of 2 is equal to 2, 3, work of 3 is the addition of the earlier 2 numbers. Work of 4 meters is the addition of 2 cases. Work of 3 plus work of 2, like this. So do it over again, then we will have the answers like this. The 3 comes from W of 3 is 1 plus 2, W of 4 is this earlier 2 plus 3, and the work of 5 is the addition of these 2. Work of 6 is the addition of 5 and 8, like this. This is recursive relations. Fibonacci sequence is similar like this, but it starts with f1 is 1, f2 is 1. Here, work of 1 is 1 and work of 2 is 2. It starts with 1, 2. Fibonacci sequence starts with 1, 1. But the recursive relation is exactly the same. Okay? In this case, 1, 1, 2, 3, 4, 5, like this. Anyway, so work of n is there's a relationship between work of robot working and is equal to f of n plus 1. If you compare these two, I will show you how it works. Here, robot working. So we made this code. I typed that code in this way. Okay, then this code works like this. So robot work 10 is 89. Robot work 3 is 2 is 2. Robot work 4 is like this. Robot work 6 is 13, 8 is like this. There are this many of the choices. For the Fibonacci sequence, like here, 10 is 50, 11 is 89. This. So that same algorithm, the only difference is start from 1 here, 1, 1 here, and start here to 1, 2 here. That's the only difference, robot working. So, okay. And mathematical induction to shows this. Yeah, we can show this hold. This is one of the relation properties of Fibonacci sequence. This is true. We can show it. When n is equal to 1, it is true. Assume true. This is true for n. Then we can write it here. Then all we have to do is show this is true for n plus 1. If for the n plus 1, if we rewrite it in here, then we can easily, it satisfies this. So this comes from the definition of Fibonacci sequence. So this is always true. Actually, there are many properties that Fibonacci sequence has. I will show it one more time in the chapter 6. I think that's the end of the chapter 4. And I already gave you the problems that you can think on chapter 4 and 5 and 6. So you just start to discuss. I think that's the end of today's class on chapter 4. Any questions? Any questions?